Okay, so today we're going to continue our discussion on nucleation processes in pure system. So I think this is what we left behind, right? In the last lecture, I think we spent most time talking about the the fundamental concepts of nucleation, in particular when applied to homogeneous nucleation, where you have, sorry, why? When applied to homogeneous nucleation, when you have, simply a isolated nucleus forming the bulk of a liquid structure, right? And in this particular scenario, we analyze that the free energy difference between a system containing the nucleus and the original homogeneous bulk liquid actually come from two contributions, right? The first contribution is the bulk free energy reduction. This is what we call that, the bulk free energy reduction due to the formation of the small nucleus, right? So if we assume that we have a spherical nucleus, and then we define this delta GV as the free energy difference between the liquid and solid state per unit volume, and then this first term here is the bulk free energy reduction, the total bulk free energy reduction associated with the let me try to use this, see if it works. Yes, I think it's probably better. So, oops, sorry. Yeah, so this whole term together is the bulk free energy reduction, right? So, and it's negative, which means that there's going to reduce the free energy of the system when you form the small nucleus. But also we said that if you look at the structure of this system containing the nucleus, there's a interface, right? That typically associated with the increase of the energy, and that's going to give you a increase of the total free energy of the system resulting from the existence of the interface, and this is going to be proportional to the interface energy, which is the energy per unit area, and then this is the total surface area of that small nucleus if you assume this is a circle or a sphere in 3 dimensions, right? And then we go ahead to analyze, then we put these two terms together, what the overall free energy difference looks like, right? And we say that first we consider we fix a degree of supercooling, we fix delta T, so this delta GV, the free energy difference per unit volume, is fixed. And then this free energy difference is going to be only a function of the radius or the size of the nucleus, right? If the nucleus is a sphere, and this is going to only be a function of the radius of the nucleus, right? And we analyze the contribution from each of the terms separately, right? So the interfacial term is going to be positive and it's going to grow as R squared, and the volume term is going to be negative and it's going to decrease as the R cube times delta T, but we fix delta T, so it's just basically going as the R cube, right? And it's very simple from a asymptotic analysis that if your system, if you're in the large R limit, right, the volume term is going to dominant because R cube is going to eventually, if you're for large R, right, R cube is going to eventually be larger than R squared, right? So, and then we know that the system definitely going to have a lower free energy for large nucleus, and for very small nucleus, you have the opposite situation, right? R squared going to be more favored because they're going to be larger. So you're going to have the smaller nucleus is not favored, and when based on this analysis, we know that this overall free energy as a function of the nucleus size has to be a non-monotonic function where you have a local maximum, right here, and we also basically analyze that this local maximum is actually what we call the critical nucleus size, because any nucleus that has larger than this R star, okay, is stable in the sense that if this nucleus is further grow or further grows, it will it leads to a lower of the free energy. So this growth is favored. Though this means that if your system simultaneously have many nucleus of different sizes, any nucleus larger than this R star can grow, right? Because its further growth is going to reduce the free energy, and we compute the value for this R star, and it's related to directly this gamma and delta GV, and also we can consider this relation between delta GV and the supercooling, okay, as the total driving force for the nucleation, and we can directly connect this R star to the degree of supercooling. Okay, so this is what we mainly went through in the last lecture. And the end of the last lecture, we also mentioned that, okay, so from this analysis, we know that the size of the nucleus is going to play an important role in the thermodynamics of the system, right? For a given temperature T, you can have a particular critical size of the nucleus. And if your actual nucleus is larger than this size, they're going to grow. And if the nucleus is smaller than this R star, they will melt back into the liquid, right? This is what we learned from this very simple analysis. And then we move on and introduce a different way of looking at this, right? So in this particular case, we'll fix the temperature and we use the radius R as a parameter to determine whether these nucleus are going to be stable or not stable, right? We say that for any particular temperature, once you fix this R star, you can definitely determine which the nucleus are stable, as long as they have radius larger than this. This is one way to look at that. Another way to look at this is that, we can go back from the size of the nucleus, from this geometry, right, back to some more intrinsic thermodynamic considerations. Okay, and this is, can be introduced through the so-called Gibbs-Thomason effect. And in a short sentence, what is Gibbs-Thomason effect? It simply tells us that there is a connection between the geometry, in particular the local curvature, or if this is a spherical nucleus, the size of the nucleus, to the thermodynamic properties of the system. So our motivation is the following, right? So if we, think about this, right? So because whenever we have a finite size nucleus, there's no way for us to get rid of this interfacial energy consideration, right? So a kind of intuitive way to consider this is that we combine this interfacial energy as part of the total free energy of the nucleus, right? So now this means that suppose that I have this delta T, right? If I have the nucleus, my actual free energy of only the solid small nucleus is given by this particular value, right? And I know that the interfacial energy in this particular case is going to increase the overall free energy of the system by this amount, right? So this means that if I look at a free energy curve or free energy line associated with a nucleus with radius R star, okay, its free energy is not this original free energy curve which we obtain for the infinite bulk solid, right, phase. And if this is already a finite size nucleus with this R star as its radius, which is just the critical radius for this delta T, we know that, okay, for this small nucleus, it will use up all of the bulk free energy reduction, which is delta GV, right? It use all of these bulk energy free reduction to overcome its increase of the interfacial energy. Okay, so this means that at this particular temperature, whatever this temperature is, Tm minus delta T, for this critical nucleus of R star, okay, this nucleus is right in thermal equilibrium with the liquid. Okay, there's no free energy advantage, there's no free energy disadvantage, right? This free energy is just equal to the free energy of the liquid. Okay, so in this sense, if you think about, if you have a particular system, right, in which the solid phase has exactly the same free energy of the liquid phase, this effectively defines the melting point for that particular solid phase, right? And the only difference here is that when we talk about the solid phase, in here, we're talking about a small finite nucleus. So this includes both a real solid phase and a interface. Okay, all these together is what we call, the new solid phase, which is a small nucleus with the interface. Okay, now, so this basically means that this analysis basically means that, if I have a small nucleus with this particular radius R star correspond to this delta T, okay, it use all of the free energy, bulk free energy reduction to overcome its interfacial energy increase. So this particular small nucleus is just at its effective melting point for this temperature, right? So that is another way of looking at this, right? So this means that, okay, you can look at the geometry, and then based on the geometry, you can basically classify, okay, any nucleus larger than this R star is stable, and any nucleus smaller than this R star is not stable, right? But there's another way to look at this is that, okay, when you have a nucleus of particular radius, okay, and this nucleus has a new effective melting temperature. Okay, has a new effective melting temperature. And this new effective melting temperature is a function of the radius of the nucleus. Okay, and for this particular guy, if the radius is just the R star, okay, and this means that this particular nucleus is right at its effective melting temperature. Okay, so and we're gonna see, if we have different size, and this will have different consequence. So this basically means that, particles with the radius R star, right, corresponding to this delta T of supercooling, used up all the free energy reduction particle is just stable at this particular temperature, Tm minus delta T. So this means that this is effectively the melting temperature for this nucleus with radius r star. Okay, so that is, another way to look at this. And now how can we use this to understand what we already know about stability of these guys, right? So we know that, okay, now I cool the system to Tm minus delta T. I still choose delta T to be my supercooling, and I call this temperature to be T star. Okay, so my T star simply equals to Tm minus delta T, which is right here. Okay, this is the system's temperature. Okay, we choose the system to be at this temperature. And we know from the free energy analysis that now if I nucleate different particles, I need to make small nucleus, right? And I might have different sizes of these nucleus because they're all stochastic. So I may have a nucleus of the size of the R star, right? I may have smaller nucleus with R1. I may have a larger nucleus with R2. Right? So this is all stochastic, so you may have nucleus of different sizes. Now from the geometrical consideration, okay, we know for a fact that for this temperature T star, any nucleus has a radius, right? Because this is geometrical consideration. Any nucleus has a radius that is larger than R star, going to be stable and further grow, right? And any nucleus has a smaller radius than R star, it's not stable and going to melt back. So we know that this guy is going to grow and this guy is going to melt back. Does this make sense to everyone? Right? This is just from the free energy analysis from the role of the nucleus and stability, right? So the consequence or the results is that, okay, any nucleus has a radius larger than R star, determined by this T star, going to grow. Any nucleus have this R smaller than R star, going to melt back, right? This is the results, the observation. Now, how can we reinterpret this observation using the so-called Gibbs-Thomason effect? Okay, now what the Gibbs-Thomason effect tells us? Well, Gibbs-Thomason effect tells us that for any particle, for any radius, for any nucleus of a particular radius, right? And you can have a well-defined effective melting temperature associated with this radius, right? Does this make sense to everyone? And you can easily find that melting temperature, okay, by finding out what is the corresponding if you have R, you have delta GV, and if you have delta GV, you can go back to find out what is the supercooling required to get that delta GV, and that is going to be the way you find out this effective melting temperature, right? So, and for each radius R, you can find effective melting temperature, right? So when I have this R star, I know the effective melting temperature is simply delta T, a T star, because this is the delta T is the associated supercooling required to overcome this free energy interface, increase of the interface energy, right? And for these two guys, I can do the same thing. And when you plug in the calculation, you're going to find a different delta T. So you're going to find a different temperature, deviate from Tm, right? So I have this for T2 and I have this for T1. Okay, so I think this is where we left behind. And the question that for you is that, okay, for this particular setup, okay, I know that the relation for the three radius is R1 smaller than R star smaller than R2. So now what's going to be the relation between their effective melting temperature, okay, in the perspective of the Gibbs-Thomason effect, right? We, associate the geometry, the curvature of the particle to a thermodynamic property, which is the effective melting temperature. Okay, now I can associate, an effective melting temperature for all these three particles, all these three different nucleus, and I call them T1, T star, and T2. What is the relation between T1, T star, and T2 if the radius satisfies this condition? So T1 is the effective melting temperature for the smaller particle, or the effective freezing temperature, for the smaller particle. That's the same thing, right? And T2 is the effective melting temperature for this larger particle. What is the relation between the three effective melting temperature given their radius?
T2 is greater than T star is greater than T1.
T1 is smaller than T star, smaller than T2. Okay, that makes sense to everyone? Does this make sense? Do we know how we can get this? So what is the relation between delta T, for example, if I have, I have all three particles, right? And we know that each of this particle going to require a particular supercooling, delta T, such that, this supercooling will induce a free energy reduction to overcome their interfacial energy, right? Does that make sense? Because they're finite nucleus, right? So they're going to have a finite increase of the free energy due to the interface, right? And we will know that, okay, at the critical temperature, all of the free energy reduction will be used up to overcome the increase due to the surface energy, right? Okay, now in this case, what is, so, and for each particle, I'll have a particular delta T, which is a supercooling that is just enough to overcome the increase of the free energy due to the interface. Now, if instead of comparing T1, T star, and T2, let's compare delta T1, delta T star, and delta T2. What is the relation between the supercooling required to stabilize each of these particles? Which one requires the largest supercooling to be stable? The smaller one or the larger one?
A smaller one.
The smaller one, right? That makes sense. So because we know that, for the smaller the particle is, the larger, the contribution from the interface. So we will need larger supercooling. So we have delta T1 in magnitude going to be greater than delta T star, right? Going to be greater than delta T2. Does this make sense? Okay, so what does this mean? This means that I have to supercool this system, more to stabilize this compared to this one and compared to this one, right? And what is T1? If I look at that, I think I should have written this explicitly. So T1 is, how can we obtain T1 given delta T1? T1 is the effective melting temperature. How should we obtain the T1 from delta T1?
Tm minus delta T1.
Tm minus delta T1, right? So this is my effective melting temperature, right? Because the delta T1 is larger compared to the other, right? So this means that T1 is the lowest among all three this temperature. And for the same reason, you can write down T star and T2, right? Similar in this form. Does this make sense to everyone? Okay, so just make sure that this is super clear because this is very important. Okay, so basically this means that, okay, now are we clear about this effective melting temperature idea? Is this Gibbs-Thomason type of idea clear? You can look at the system different way, right? If you look at the geometry, we know, that if you have the system with T star, and from this T star, you can easily compute a supercooling delta T, and from this, the critical radius R star. And we know that, okay, any nucleus with radius larger than this are still going to be stable, and any nucleus with R smaller than this is going to be unstable and melt, right? The Gibbs-Thomason effect is going to give us a different way of looking at this, right? Instead of looking from the geometry point of view, we look at thermodynamics. And we know that for each radius, we can definitely associate it with the effective melting temperature. And in here, from all our analysis, we know that effective melting temperature for these three nucleus is T1, T star, and T2. And they have the relation that T1 smaller than T star, smaller than T2. Is this crystal clear to everyone up to this point? Okay, cool. So I got a question from the chat. So how large is R star, T star? This depend on the degree of supercooling. So this if you choose delta T to be minus 5 degrees Celsius, I would say R star going to be like maybe a few nanometer. I don't know exactly, but it depends on the supercooling. But it's very, very small in size in general. Just in terms of atomic level, it's just a large cluster of atoms, but on a macroscopic level, it's kind of small. Okay, but anyway, so this wouldn't affect our analysis. So this is T1, T star, and T2, right? So we know this. And now let's use this thermodynamic, idea to see whether we can still rationale or still come to the same conclusion that we get from the geometrical analysis, right? So now if we say the system is imposed with a temperature of T star, okay, have the temperature of T star. And if the melting temperature of this guy, this larger guy T2, is larger than T star, what's going to happen to this guy? So I'll give you some numbers. Okay, so if my T star equals to minus 5 degrees Celsius, this is the degree of supercooling that I imposed, right? I imposed 5 degrees of supercooling. So my T star compared to, this is water, for example, my T star going to be minus 5 degrees Celsius. Does that make sense to everyone? Okay. Now my T2 is higher than that. So I just choose T2 equals to minus 3 degrees Celsius. So that is the melting temperature of my R2. Does that make sense to everyone? Okay, so this means my melting temperature of R2 is higher than the actual temperature that I impose. Now, what's going to happen to my system? What's going to happen to this R2? Does this R2 grow or shrink or stay the same?
It
Grow.
will shrink.
Okay, so
What,
melting.
No.
Yeah, go.
What was the question that you about R2? Sorry, I was trying to think about it, but
Yeah, the question is that, we know that from the Gibbs-Thomason, from the our previous analysis, we know the radius is going to determine the fate of the particles, right? This is clear, right? We know that, for this supercooling delta T, we have the system of a temperature T star, and this supercooling is stable, is just enough to stable any radius of R star, right? This one is just a stable. So from the geometrical point of view, we know that whenever this GR, the radius of the particle greater than the R star, they're going to grow, right? Any particle smaller than R star are going to shrink, because we know this is because we're doing this analysis. This is what we did in the last lecture, right? We know that how the free energy change as a function of the radius, and we select this critical radius together, and by calling the critical radius, because we know any radius larger than this is going to grow and smaller than this is going to shrink, right? This is what we know. And now I'm trying to introduce a new concept of looking at this, right? So we know already from that free energy analysis, from the radius alone, we can determine the stability. But how about we associate the radius to some thermodynamic properties? Okay, this is the idea of Gibbs-Thomason effect, because this will turn out to be very useful later. So we associate the radius to their effective melting temperature, right? And this is, I think, is already clear as we spend a lot of time on this. And this is what we get. Right? So we know that if you have a larger radius, you have a higher effective melting temperature, T2. If you have a smaller radius, you have a lower effective melting temperature, T1. Now, we're trying to use this, we're not considering the effect of the size of the particle. We're looking at the melting temperature, right? We want to see, okay, now we are using the way, we're using the logic of Gibbs-Thomason effect, and we're not working with the radius anymore. We're working with the temperature, okay? Can we get the same result as if we're using the radius to analyze the fate of these particles? So what we know about the radius, if R2 is greater than R star, we know R2 is going to grow, right? This is based on our free energy analysis. We know that this radius is going to be stable. So the fate of R2 is to grow. Can we get the same conclusion from the effective melting temperature analysis? Okay, so if I choose my T star to be minus 5 degrees Celsius, I choose my T2 to be minus 3 degrees Celsius, which satisfies the condition that T2 is greater than T star. What is the fate of this R2 particle? Does it grow? Does it go back to the liquid?
Wouldn't it, if you're increasing the temperature, wouldn't it just grow until it hits its melting temperature?
No, I choose the melting temperature to be, this T2, for example, is fixed to be minus 3 degrees Celsius, right? And my T star, which is the temperature of the system, is minus 5 degrees Celsius. Under this condition, will the particle R2 will grow?
Yes.
No, it'll melt.
It will grow, right?
Yes.
Because if think about this, what does this mean? This means that if I have a cup of water, which we know that this water is going to freeze at 0 degrees Celsius. Now I cool the system 2 more degrees. I cool the system to minus 2 degrees Celsius. Will the water freeze, or the water will remain to be water? It will freeze, right? Because you impose a supercooling. That makes sense to everyone? Let me write down this. So this is
I'm a little confused. You said that the melting temperature of T2 is -3, and if the system's at -5, it'll grow, shouldn't it?
Yeah. See, the system, what is the temperature of the system? Is the temperature of the system higher or lower than the required melting point?
Oh, you were saying okay, sorry, never mind. I was just having a dumb moment.
No, it's okay. So this is a confusion that I know that this part will confuse most of us, because I was confused about this for a long time. But anyway, you see, this is my T star, right? So T star is lower than T2. This is your melting temperature for this guy, right? for this guy. And you have a temperature low. Yes, right? It will further grow. Does that make sense to everyone? Is this clear? So this is the same conclusion that we get from analysis of the radius, right? So you see that this is consistent from the Gibbs-Thomason effect. We convert the geometrical effects, which are the radius or the curvature, to the effective melting temperature. And now we focus on the effective melting temperature. We see everything is consistent. Is this point clear to everyone? Okay, I hope so. Let me do more. Okay, so now if this particle further grow into a slightly larger radius R3, is this particle still stable with this larger radius? So for this larger radius, you can get a higher T3, right? Is the T3 higher than T2 or lower than T2?
It's higher.
It's higher, right? So this means that if you keep the system at this temperature, the system feel a larger supercooling when it grows larger. Does that make sense? Because now your T3 may already be -1 degree Celsius, right? Because you're even larger. Okay, that makes sense to everyone. So this means that, okay, so you can grow, and as you grow larger, you become more and more like to grow because you feel larger and larger effective supercooling. Does that make sense to everyone? So
Yes,
I think this is yes. So what is the largest supercooling this guy can feel? So if I keep on growing, right, I can become larger and larger and larger and larger. What is the largest I can become? What is the largest R I can go?
Oh, T star, right?
T star is the melting temperature. What is the largest supercooling? Now let's follow my way of thinking. What is the largest size of this nucleus you can go?
Won't it continue to grow until it fills the whole box?
Exactly, it fills the whole box, but from atomic level, when the particle becomes macroscopic in size, we can effectively say this guy goes to infinity, right? If we have a very, very large system. Does that make sense to everyone? Effectively, right? This is a little tricky. So what is the melting temperature for a particle with a radius that goes to infinity? Infinitely large bulk solid. What is the melting temperature for this guy? Let's call this T infinity. This is water and ice. What is T infinity?
Wouldn't it just be the same, like the regular melting temperature that's on the graph for that first line?
This is gonna be Tm, which is gonna be 0 degrees Celsius. Does that make sense? So basically, you see when the particle goes to infinity, right? There's no geometrical effect, there's no curvature anymore, and then your thermodynamics just goes to the normal thermodynamics we all know, and then the melting temperature, the effective melting temperature, is just a well-defined thermodynamic melting temperature, right? So what is the degree of supercooling this guy now feel? Now, if I cool, I have a nucleus which is already, with the size of the box, what is the supercooling it feels? What is delta T infinity?
0.
0.
-5, right? What is delta T? Delta T is T star minus what? T star is my temperature, right? What is delta T? Tm, right? And this Tm should be considered as what? As the effective Tm, right? Because particles of different sizes are going to feel different supercooling, right? Because we start from this R2, right? For R2, what is the effective melting temperature? We just choose this number, but say this is -3 degree, right? So what is the supercooling it feels?
S5.
No, this is the system's temperature. So it has like a 2 degree of supercooling it feels. My delta T equals 2, right? Does it make sense? So I think I need to change that. Does this make sense? I think I need to change this a little bit. So delta T equals to effective melting temperature minus your T star. T star is the temperature you impose, let's say, right? I'm looking at this R2 particle, right? In its original size, we know that this feels the supercooling of 2 degree, because this T2 is the effective melting temperature for the particle with radius R2, right? This Tm is the temperature I impose. So Tm is always T star is the temperature I impose. I keep it to be a constant all the time, right? This does not change. And the only thing change is the effective melting temperature, which is a function of the radius of the particle, right? Now, when the particle has radius R2, its effective melting temperature is -3 degrees Celsius. So what is the delta T for this particle?
+2.
Delta T is 2, right? I take -3 plus 5,
plus
right?
5.
It's 2, right? This is 2 degrees of supercooling. That makes sense to everyone? Okay, and now say the particle grow a little bit to the radius of R3. Now, we can do the calculation, but I'm just imposing a number. So for this R3, my effective temperature increases, right, to -1 degree. Now, what is the supercooling I feel?
+4.
4. I feel larger supercooling because I'm more, the effect of the interface gets smaller because I'm larger. Does that make sense? Okay, and finally, if I go to infinity, what is the supercooling I feel? -5, because now my this should be +5, sorry. So because the melting temperature now is 0, right? So all of the cooling that all of the initial imposed supercooling is already, I can use all of this to reduce my free energy for the system because I don't have any effects of interface because I'm infinitely large. That makes this whole analysis make sense to you? Okay, so you see the things that play important, roles here are, the interface, right? And the existence of interface will increase the energy of the system. Okay, so depending on the size of the nucleus, it's going to use different portion. It will use different portion of the supercooling that you initially impose in order to cool the system, right? And the interface is going to use some of those. Okay, so whether you can further grow or you're going to shrink depending on what are the remaining supercooling, right? So because for the original system, we impose a 5 degree of supercooling, right, compared to the infinite bulk phase. But we know that if you have a finite particle, like radius R, my supercooling now becomes only 2 degree. So I use 3 degree of the supercooling in certain sense to overcome my interface energy. So I can only use the remaining, which is only 2 degree. That makes sense to everyone? Okay. So in general, this is again, I think we need to move on, but this is in general what the Gibbs-Thomason effect is about, right? So the thing is that you convert the geometry into thermodynamics, right? So we convert geometry to the effective melting temperature. Now, what is the advantage of this? Well, first, it gives us a consistent analysis as we did based on the radius of the particle to test its stability. And second, as we will show later, it will give you a quantitative relation between what are the effective supercooling you can still feel. Okay, so because for now we don't have to introduce that equation, but I just want to make sure that this is clear. Why we introduce the Gibbs-Thomason effect, because eventually we're going to get something like that. Let me write down this for you, and we're going to revisit this, right? So now a particle with a particular radius is going to feel a supercooling that is a function of the radius, right? And this supercooling is only be a portion of the original supercooling I call delta T0, right? And then this, I think, I can't remember exactly, but I think it's going to be given by this. This is your R star, okay? And this is going to be your R. Okay, so this is, I think a key results from the analysis of the Gibbs-Thomason effect. So why we introduce the idea of temperature? Because we want to see how much supercooling I can still have, because this is going to be the effective driving force for the nucleation and for the growth of the small nucleus. And we're going to use this a lot. Okay. That this makes sense to everyone? I just want to make sure, again, we don't have to, it's very easy to show this, but for now, I just want to, make sure that we understand the logic behind this and the meaning of Gibbs-Thomason effect as it applies to this effective melting temperature. Are we clear on these aspects? Okay, so okay, I think that's that. Okay, it's not done yet. Okay, so we'll just look at one particle, right? Now, how about this particle? If you look at this particle, Okay, what is the supercooling this guy feel? What is the effective melting temperature for this guy?
It's 0 because you have T star minus T star.
Exactly, because this effective melting temperature is T star, and you cool the system at T star, so this guy has no supercooling, right? This guy does not feel any supercooling. So this is very much like that. You have a cup of water or you have a cup of ice, whatever. You keep the system at 0 degrees Celsius. You wouldn't see any phase transformation because at this particular temperature, the solid phase and liquid phase are equally stable, right? So this particle, in principle, it wouldn't grow and wouldn't shrink. If there's no perturbation at all, this particle is going to remain to be this particular size forever. Does this make sense to everyone? Okay, now you can also check from here. Okay, so this is the effective supercooling you feel for a particular particle size. When you plug in R equals to R star, what do you have? Am I jumping too fast? So from this analysis, we see that if you have the radius particle of radius R equals to R star, it feels no supercooling, right? Because we impose temperature to be T star, and the effective melting temperature is also T star, so you have no supercooling for this guy. Okay. Now, I'm just asking to check this equation. What do we have if we plug R equals to R star here?
You get 0.
You get 0, right? Because this factor gonna equals to 1, and you have 1 minus 1, you get 0. That makes sense to everyone? Okay, let's do one more check. So if R goes to infinity, what do you have? Oops, sorry, this is supposed to be infinity. What do you have for the supercooling?
Delta T naught.
Delta T naught, right? This is just based on normal thermal analysis. If you have an infinite bulk system, and this is the supercooling you have, right? And this equation does not define, or you can consider it's defined also in a certain sense, but not real physical sense. What happens if R is smaller than R star? If you look at supercooling, what happens if R is smaller than R star? What is this factor? What is this ratio? If R is smaller than R star, what is this R star over R going to be? Greater than 1, equal to 1, smaller than 1?
Greater than 1.
Greater than 1, right?
The numerator is
This
larger.
one is smaller, this one's larger. So this whole thing is going to be greater than 1. And you have a 1 minus a number greater than 1, you're going to get what? A negative number, right? What does a negative supercooling mean?
You're heating the system?
Exactly, or too hot, right? That makes sense. So supercooling means what? I cool the system below the melting temperature. And now if the supercooling is negative, this means that my temperature is actually higher than the melting temperature. Does that make sense to everyone?
Wait, so is that saying that to get a particle like T1, you have to heat it up? Or
No. You didn't have to heat it up. It means that the T1 feels like it's not happy because it's too hot.
Oh, gotcha. Okay, that makes more sense.
Right. This T star is my actual temperature. This is the temperature I want. This is the temperature I want, right? But my actual temperature is higher than this temperature. So this means that this guy feels too hot. It won't stay, it's too hot for it to stay in a solid form. So it's gonna melt back. So to feel, but we typically do not apply this to negative R because it can be applied to this because if you look at the relation, it's all linear. So this applies as well, but we typically don't say that, because we're not, analyzing a negative driving force. We can only say that, okay, if your radius R is smaller than R star, this is going to give you a negative supercooling, which means that the environment is too hot for this particle to grow, to remain to be a solid particle. It's going to melt back. Does this all make sense to everyone now? Okay, so I do hope so. But I think it's worth the time. So basically, again, what is Gibbs-Thomason effect? You convert the geometrical consideration. We can now easily make a conclusion if we know what is R star and we know that you have R1, R2 based on the relation between R1, R2, R star. We can easily determine the fate of each of the particle, right? From our original free energy analysis. Again, go back to this picture, right? We already know this, and now we move one step forward, right? We convert using the Gibbs-Thomason effect consideration. We can convert the geometry effect, the curvature effect into effective melting temperature, which are these guys, right? And from this effective melting temperature, we can move one step forward to work out what is the actual or effective supercooling felt by each particle. And that supercooling will be the driving force for nucleation growth. We'll see later. But for now, it's just good to appreciate that you can convert the radius and the geometrical consideration of the particles into thermal considerations as the effective melting temperature. And use this information, we can get exactly the same conclusion about the stability of the particles, right? I think in a more elegant way, because you just consider melting temperature, compare the melting temperature to the current temperature. It's fairly straightforward to consider the fate of the particle, right? So now what these here are the same thing that we already considered, right? So this dashed line gonna give you T star, okay? And then this red line and this blue line correspond to the melting temperature to either R1 or R2, okay? Now I'm going to ask you if we understand this correctly, okay, what this line corresponds to. This blue line corresponds to the melting temperature of R1 or R2.
R1.
If this corresponds to R1, does R1 grow or shrink? Because my temperature is right here. This is my current temperature, T star, right? This is my T star. If I have this temperature, is this temperature higher or lower than T star?
Lower.
This is the increasing temperature axis. This is
Higher
0.
temperature.
This is -5. And from left to right is increasing temperature. So this blue line, okay, if we focus this blue line, does this correspond to a temperature higher or lower than T star?
Higher.
Higher than T star, right?
Yeah.
So this means that if I have a particle with this temperature, does this particle feel a supercooling? Does the particle happy and will grow?
No. Because it's higher than T star. It's hotter.
This is my T2, okay. So let's write down this again. So T2 equals -3 degrees, okay? T2 is higher than T star, but does the particle at T star, so this is my R2, right? Does this particle R2 happy or not? Does this particle feels hot or feels cold if I cool the system to -5 degrees Celsius while the particle only needs -3?
Oh, then it would feel cold.
The particle feels cold, right? Because I have a supercooling, which is this, because I cool the system lower than what I need for the particle to be stable and to grow as a solid. Does this make sense to everyone?
It makes
Okay.
sense, but like, what does that mean for the particle at that point if you overcool it?
It will grow because you have the supercooling. It has a driving force to further grow.
Oh, okay, yeah.
Right? That makes sense. That's the whole point of delta T, right? That's
Yeah.
the whole point we introduce the supercooling. Okay, that makes sense. So this line corresponds to T1, T2, and this one corresponds to T1, right? For R1. So what does this particle feel? Does this particle feel too hot or too cold or just right?
Too cold?
This particle will feel too hot or too cold or just right?
Too hot.
Too hot, right? Because this is -8. I need -8 to crystallize, but now it's -5. This means that my temperature is 3 degrees higher than what I need. So it's too hot for this guy. So what's going to happen to this smaller particle?
It will melt back.
It will melt, right? Because if it's like that, you're keeping ice at 3 degrees Celsius. It's eventually going to melt. It's too hot for the ice to be stable. That makes sense to everyone. I think that I get the lines. I think this makes sense, but it's still very confusing. But again,
But the temperature is decreasing, like -5 to -8. Then
no, the temperature is not decreasing. The temperature is kept at -5.
oh,
This is imposed temperature, and now I have nucleus of different sizes. Because they have different sizes, they have different intrinsic effective melting temperature. So they feel the same temperature, but it means different to these particles. Okay?
okay.
It's all -5 degrees. That's the system's temperature. I fix this to be -5 degrees, but I have particles with R1, and this particle feels too hot. And I have particles with R2, this particle feels too cold. So it's very happy to grow. And I have particles of R star, and this particles feels all right because it's not too cold, it's not too hot, it's just right, so it won't grow, it won't shrink, it just remain to be of its original size without any perturbation. Does this make sense?
Yes.
Good. So let's move on. So again, this is I understand. I said this is from the many years of teaching. I know this is a very confusing concept, but will be very helpful, in our later analysis, because we can easily get the effect of curvature on the degree of supercooling, and supercooling is the driving force for the growth. So we can easily connect, a lot of interesting properties, because for a particular supercooling, it will select the different curvature to grow. You'll see all these instability patterns, things like that. And the fundamental to understand those, later more complex events and complex phenomena is the Gibbs-Thomason effect. We have to really understand this. Okay, so I'd rather, because we spend a lot of time on this, we record the lecture, so I think we will have good material that you can review again. But make sure that you do understand this. I think this is one thing that I really want you to get out from this lecture. After many years, if you forget everything, but I still hope that if someone mentioned Gibbs-Thomason effect to you, you can still ring a bell. Okay, that would be, perfect. Okay, good. So let's move on. This is, I think pretty much all I want to say. So what is the Gibbs-Thomason effect? In summary, this means the local curvature affects the effective melting temperature of these particles, and that's the effective supercooling felt by each of the nucleus. That's basically the Gibbs-Thomason effect in a nutshell. Okay, and we're going to make this, as we said, for now we focus on the conceptual understanding. Later we're going to make this more quantitative. Okay, and we already show you the equation for that, but we'll show how we get that, which is very straightforward. Okay, so let's move on. Okay, again, so for what we have for now is that, okay, we derive this. This is one key result we have, right? So basically from the size of the nucleus, we can determine which particle going to be stable, which are not going to be stable, depending on the size. And then we move on to talk about the Gibbs-Thomason effect, which is a different way of looking at stability, but not on the geometry, but from the thermodynamic point of view, right? And we show how they're going to be connected. So, up to this point, we have been focusing on this R star a lot, right? We've been focusing on the critical size of the nucleus. But remember, we still have a very important thing, which is this delta G star, right? What do we call this? This is the effective, energy barrier for you to make the nucleus, right? We have been focusing on the R star for all these discussions, but, are we forgetting about delta G star? Okay, what is the role delta G star going to play in the nucleation? Okay, so I think I briefly mentioned this a little bit, right? So I say that, okay, so the nucleation process is a stochastic process due to the fluctuations. And at any time point, you may have large nucleus like this, you may have, smaller nucleus like this, and you may also, if you're lucky, have nucleus of this right size, right? But which of the nucleus do you think is more easier to form? Is the larger ones more easier to form, or the smaller ones are easier to form?
Smaller ones are easier to form at first.
The smaller ones are easier to form, right? Because why? Because if you form a smaller one, you just need a really lower energy barrier. Does that make sense to everyone? Because up to this point, right, if you further larger is fine, but up to this point, the smaller the nucleus is, the better you have, right? Because it's going to give you a lower free energy, and it's easier for you to get energy fluctuation that is comparable to this energy barrier, so we can form the nucleus. Does this make sense to everyone?
Yes.
Yes.
Okay. Yeah. Right. But are the smaller ones useful? Are the smaller nucleus really useful? Where am I? Oh, I'm sorry. M2. Are the smaller ones useful? If you look at this, they're not, right? Because you wouldn't see these guys because they form and they're gonna melt back, right? So what are the ones that are really useful for us for the nucleus to grow, for us to see the system have nucleus? You should at least have this guy, right? Does that make sense?
Yeah.
So this means that in order for you to see the system start to nucleate, you can always have these smaller nuclei forming all the time, but they're not going to be helpful because they're going to melt back, wouldn't contribute to any subsequent phase transformation. So the minimum energy you need is going to be this guy. So you would need some fluctuations that is at least as large as this delta G star to give you a nucleus as least as smaller as this guy, right? And then you can further grow. So this means that my delta G star is a very key energy consideration, energy barrier, okay, that contributes really to the nucleation, because any nucleus smaller than this wouldn't actually contribute to the phase transformation. Okay, does this analysis make sense to everyone? Okay, so I have to assume that makes sense and move on. Okay, so what this means, okay, because the nucleation formed a flocculation against the energy barrier, and we said that, okay, it's easier for the smaller nucleus to form, but it's gonna be helpful, right? Only the particles that overcome this barrier will contribute to subsequent transformation. Only the particles that form, go over this energy barrier are the ones that we eventually can observe in the system. Okay, so the number of those particles, okay, typically we call this nucleation rate, or number of the nucleus in the system is proportional to basically this Boltzmann factor, right? Does this make sense? So the KT, again, is the thermal flocculation, it's the energy, of the system that you can use to extract to overcome this barrier. And the key barrier is this guy, right? This delta GR when R goes to R star, because that is going to be the key, size of the nucleus that you're going to see them and contribute to subsequent transformation. Okay, so we're going to plug delta G star in here. Okay, and that because that is basically the nucleus you're going to basically observe and contribute. So you plug in delta G star, I think in here, it's pointing to the right direction, but you get the idea. Okay, and when you plug in this, and we basically use the relation between delta G star and the degree of supercooling, we can write down this Boltzmann factor. A naught is just a constant depending on the material. Boltzmann factor in this form. A is a constant, but you see that you have a exponential term and then within this you have a quadratic of the degree of supercooling. Okay, so what does this mean? I want to go through the details. It's pretty straightforward, just mathematics. This means that your nucleus is super sensitive to the degree of supercooling. Okay, because it's in the exponential, it's minus quadratic. Is 1 over the quadratic function, so it's very sensitive. And again, I think this is, I don't know why I'm not seeing this clearly, but if you do the plot for this guy, and you choose a particular material system, and you will see that the nucleation, the nucleation rate, okay, it's very sensitive to temperature. So basically, this means that at a particular temperature, you didn't have nucleation, and suddenly, if you change the supercooling, if you increase supercooling, and everything boom come out. Okay, so it's come out very quickly. Okay, so this is kind of consistent with our intuition. So it's like that if you keep the system like a cup of water at 0 degrees Celsius, you wait for a very long time, you don't see anything, right? But you just cool the system a little bit lower, and suddenly you'll see everything emerge very quickly. Okay, so that's basically going on here. So the nucleation rate is super sensitive to the degree of supercooling. So as you go from 0 supercooling to a large supercooling, you'll see that this can emerge. All the nucleus can suddenly emerge very quickly. Okay, so and that is I think the last thing I want to mention about homogeneous nucleation, and you'll see how this energy barrier come into the play. Right, we know that the radius is going to play an important role in determining the stability, and the energy barrier determine the rate, how fast you can make these smaller nucleus in the system. And then this is relation between the degree of supercooling. Any questions before we move on about this? Okay, I think this is clear. This one is pretty clear. So let's move on. Okay, so this is about the homogeneous nucleation, right? So again, the 2 key ideas that I want for this lecture is this guy, like this free energy analysis, right? From this analysis, we get 2 important quantity, R star and delta G star. And if the R star, we subsequently discuss the Gibbs-Thomason effect, right? And delta G star going to contribute to the nucleation rate. Okay, so that's pretty much everything in a nutshell that we have discussed for the homogeneous nucleation. Okay, so now we're going to move on. So and this is based again on our intuition and observation. So if you put a cup of water right in the refrigerator, if you have the required supercooling, right, to allow the system to really do the transformation, if you happen to look at during the transformation, okay, and eventually what you're gonna see ice form within that water, right? But where did you see the ice form first? The ice form just emerge in the middle of the liquid, or the ice actually they start to form at the wall of the cup, from the bottom of the cup, and then start to grow in that direction.
Wall and bottom.
Wall and the bottom, right? This is, I think, is pretty is quite a kind of intuitive because I sometimes, you know, especially at Arizona during the summer seasons, I want something cool, right? I put a cup of, you know, Coke in the refrigerator. I want it to cool down, and when I take it out, I see a lot of ice on the surface on the wall of the cup, right? I don't see anything within the bulk, or there might be something within the bulk, but I will say probably that because the ice break off from the surface and flow in the bulk, but it's not forming the bulk, because you can see that from the shape. So anyway, so we see that, you know, in most of the cases, if you talk about container, right, you talk about the wall, you know, the nucleus or the solid is more favorable apparently to form on the container, on the wall at the bottom of the container, right? So we call these heterogeneous nucleation because it's not that you have a pure solid nucleus formed within the bulk. It's that you have a solid involving existing interface, right? And it's kind of interesting because if you already say that, you know, you see more of these nucleus, you see more of the ice formed on the wall on the bottom. This means these you know, nucleus, these heterogeneous nucleus are more easier to form. Does this make sense? Right? Because that's why, you know, you see more of them, you know, and simply this means that their nucleation rate is higher per unit time. You have more of these heterogeneous nucleus form, right? So does that make sense to everyone? Right? We don't have to do any calculation, but just based on this observation and what we already know about the factor determine the nucleation, we already know that, okay, it's more easier for these guys to form. So this means probably they have a lower activation energy associated with them.
Professor?
Right.
Professor?
Yeah, yes.
Could you please say one more time what is the difference between a homogeneous and a heterogeneous nucleation?
Difference right here. So the homogeneous nucleation is that you have a very clean homogeneous nucleus forming in the bulk within the liquid. So you just need to worry about solid, liquid, and interface. And this interface is only between the liquid and solid. And here you have to worry about solid, liquid, and the wall or a third-party interface, right?
Okay, thank you.
Yeah, and what we're trying to figure out is that, you know, why it's more easier for the heterogeneous nucleation to occur, right? And before we do any analysis, from what we know about nucleation rate, because you see more of this per unit time or in a given time period, this means that they have a much faster nucleation rate, right? And from what we know about the nucleation rate, we know probably this heterogeneous nucleation, this guy gonna only involve a smaller activation energy. This is our logic right now, okay? So yeah, is that clear to everyone? So now we want to do something more quantitative. Why, you know, if you have a heterogeneous nucleation, you have a lower activation energy, because this is already from what we observe and use a very simple reasoning. This is what we conclude. Now we're going to show why this is the case. Okay. So again, what are the key for us to analyze the nucleation processes? What did we do in this case, in the homogeneous nucleation? What is the driving force for the nucleation, for the phase transformation?
The temperature and particle size.
But more fundamental are the free energy, right? The free energy analysis. So basically what we did here is that we write down the free energy difference between this particular system and the system with pure water, right? Pure liquid, and we get a difference. And what do we have for here? How many terms do we have? We have free energy contribution from the bulk, right? And we also have free energy contribution from the interface. So we know that these two different things are going to contribute a lot to our analysis, right? And then we should basically, based on the experience we have here, I think the first thing we need to do is to identify the bulk phases and the interface. Does this make sense? Okay, so the bulk phase are quite clear. So we have a liquid right here and we have a solid right here, okay? And we don't have to worry about the mode because the mode remains to be the same before and after transformation. So they wouldn't contribute to any bulk free energy difference. But now if you look at the interfaces, this is quite interesting. How many type of interface do we have here?
3.
How many types of interface do we have in here? I'm sorry, I think I just lost connection.
3.
3, right? So we have the interface between the solid and the liquid, right? Which is, I don't know which is the order I showed, but this is an interface between the solid and the mold, right? Between the solid and the wall, right? The one I showed using red, okay? And we have the interface between the solid and the liquid, okay? And are we missing anything? Don't forget that we also have the interface between the liquid and the mold, right? Now, of course, if you just look at this guy, it appears that we don't have to involve this part because it does not change. But if we do not have this guy before, okay, remember that this part, this red part, okay, after we have this nucleus, now the red part is the interface between the solid and the mode. But before we have this nucleus, what does this red part correspond to? The interface between the solid, the liquid and the mode, right? So we replace some portion of the interface between the liquid and the mode with the interface between the solid and the mode, and this is going to contribute, to the free energy difference. Okay, so that I have to move on a little bit quickly. So before we move on to talk about the free energy difference, I just want to write down this equilibrium condition for the surface energy or surface tension. Okay, so we have been calling this the surface energy, but if you check it, it actually has the same unit of force per unit length. Okay, so that's basically the definition of surface tension. So and they're physically are basically the same thing. And we can actually, based on this interpretation, we can write down an equation that talks basically gives you the magnitude between these energy terms, the interfacial energy terms. So because we know if we have an embryo like this, right, we have anything like that, and if this point is stable, okay, and this point will actually feel three forces, okay, due to the surface tension or surface energy. Because if you ever play with that, you have a below the bubble using some soap water, okay, why you have bubble? Because the surface energy, the surface tension wants to minimize the surface, right? And that's why that eventually have a bubble, it evolve into in equilibrium, a spherical shape. Okay, so now if we look at this particular point, okay, and it appears to be stable, but this is a delicate balance between three different surface tension or surface energy minimization. Why is that? Because if you look at this point, okay, and think about the interface between the mode and liquid, what the mode and liquid wants to do about this point. It wants to pull the point to the left, right? Because this will locally minimize the interface between the liquid and the mode. Minimize this interface. Does that make sense to everyone? So the overall rule of the surface tension or there's interfacial energy between the liquid and mode wants to pull this point to the left, right? And for the same reason, okay, and the solid and mode interface wants to pull to the right because this is gonna minimize this red part, right? This interface energy, this total interface area, okay? And for the same reason, okay, the interface energy between solid and liquid wants to pull in this tangent direction because this is gonna minimize its own surface, okay, or its own interface. And all through these ways, they all can reduce their interfacial energy, right? And that if this is not on the interface, but in a bulk water, that eventually the solid, this interfacial energy can evolve the particle into a spherical shape minimum, because that's the minimum surface energy you can have for any given volume. Okay, now in this case, because you already have this condition, so we can write down this in equilibrium, when the shape does not change, this means that this point is at balance, right? The force are balanced at this point. And in 3 dimensions, this should be a perimeter, but at each point locally, the forces equals one another, balance one another, and you can write down this relation. Okay, so this means that we focus on the horizontal direction. Okay, we focus on the horizontal direction, and the surface tension pulling to the left is balanced by the overall surface tension pulling to the right due to the surface mode interface, solid mode interface, and the component of the surface tension between the liquid and solid, okay, along the horizontal direction. So we have this equation holds. Any questions up to this point? Okay, and then this allows us to write down a very useful quantity, which is this theta, right? Because what is theta? Theta is basically an important parameter to determine the geometry of this solid, right? Okay, we assume that in our analysis that this part, this particular what we call embryo or cape, okay, is a part of a circle that you cut through. Basically you have if you have a circle or 3 dimensions, you have a sphere, you just cut through the sphere and then keep a very small spherical cape. Okay, and that is what we have for the shape of this embryo. And I think in the next slide I'll show you the geometrical model for this. And then key parameters determine, or the key geometrical parameters for this embryo, the spherical cape, okay, involves the radius of the original sphere, and then this theta, because you know these two quantities, you can write down the surface, volume, and all of the things about this guy. Okay, and then from the balance of the surface tension consideration, we can easily obtain this important geometrical parameter theta. Okay, and because for a given material, you have results, you have data for the surface tension. For example, if you have water and ice, and then you have a particular glass cup, and you can easily find out what are the surface tension among these three, or the interfacial energy of these numbers. So you can compute what is equilibrium angle theta or cosine theta for this. Okay, so once we know the free energy, okay, let's once we clear about the geometry of this, let's talk about the free energy change. Okay, again, you have to compare this whole configuration with one that you didn't just have liquid and mode, right? But because we already worked out this guy, so we know that there will be contributions from the bulk, which is this one, right? So del GV is what is the free energy difference per unit volume between the bulk and liquid, and Vs is the total volume of this small embryo, more small nucleus. Okay, so this corresponds to the bulk free energy reduction. Okay, does this make sense to everyone? And now we consider two interfaces. If you just focus on this guy, in this particular consideration, how many interfaces do I have for the nucleus? I have two types of interface, right? One is the interface between the liquid and solid, and the other interface is between the solid and the mode. Does that make sense to everyone? And of course, they have different areas, right? This is the surface area of the spherical cape. This red one corresponds to the area of that pure circle, small circle that you cut through the whole sphere. So they have two different areas associated with the corresponding interfacial energy. Are we done here? Are these the only considerations of the energies we should put into the equation?
No, liquid and mold is also count.
Exactly, because you see this interface, this red one is not a created interface, right? So this blue one is a newly created interface because before it didn't have any solid. But this red one is not, because even before you have a solid form here, you already have interface between liquid and mold, right? So you compare the energy for this part, you're not just comparing zero energy. So you should actually compare the energy associated with this particular interface associated with the liquid and mold interface before you have the nucleus, right? So for that one, you have to take away the original interface energy in the system. So we have a new term here, right? This is kind of another difference between heterogeneous nucleation and homogeneous nucleation. You have more interfaces, and you have to consider different type of interfaces in the nucleus, but also when you compare the free energy of my current system and your original system, you have to also consider originally already have some interface, and this interface has been replaced. So the solid mode interface, this area is the same, but before the transformation, before I form the nucleus, the interfacial energy is different, right? So these two terms have the same surface or the area of the interface, but their energetics are different. So that's the new term that we have to take into account. Okay, and that is all the energy terms associated with the nucleation processes. And now if we write down this, the next step will be straightforward, right? So if we again assume that this is a spherical nucleus, part of the spherical nucleus, right? This ideal shape of the cape of the nucleus. As we said before, you have the radius r, and then you can define the geometry for this circle we call a, and the height for the cape called h. But all of these are related to the important factor we call theta, which is this angle, right? And you can easily work out a relationship between h, a, and r using theta. And we know what is theta because once we know the system, we can actually compute the theta from the three surface tension considerations, right? So this means that for any given system, in principle, I can work out the geometry of this nucleus very easily. And I actually will leave this to a homework problem for you after the midterm, so you don't have to worry about right now. But I give you all of the geometrical relations because now you have to compute the volume of the spherical cape, right? You have to compute the surface, the surface of the cape and the surface of this bottom circle, and then the equations are all here. You can easily, work out. After I will say not very difficult, but a little bit sophisticated mathematical operations, okay, and it turns out that the this overall difference of energy, okay, for the heterogeneous nucleation have this very beautiful term, okay. Now, if you forget about S theta, just to look at this, does this look familiar? Just look at it's the free energy, the free energy difference for the homogeneous nucleation, right? So this is the bulk free energy reduction of a particle of the nucleus of radius r, and this is associated interface energy contribution. And this is we'll only have one energy area consideration here, which is the surface liquid interface. Okay, we do this through the simplifications because the solid liquid interface energy is the only intrinsic quantity here, right? Because I can put my water into a glass cup, I can put it in a plastic cup, I can put it in a metal cup, it doesn't really matter. But liquid and solid interface is the intrinsic quantity here, so we keep that. And by keeping this, we can write down the this energy difference, okay, in a very elegant form, which can conclude basically this is a part of the homogeneous nucleation energy, right? And then a function involving theta. Again, theta is just determined by the balance of the interfacial energies. Okay, and then I give you the expression for the theta. Again, you have a homework to work out this in detail, but it's not too difficult. But I give you the theta like this. Okay, because we're running out of time, so I can directly jump to the conclusion. If you analyze the value for this theta, okay, you'll find out that you can do the plot and do the local minimum analysis. You'll see that this function can always be smaller than 1, but greater than 0. Okay, so what does this mean? This part is the homogeneous nucleation energy for the particle of the same size, right? Same radius. And then it has another factor multiplied to this overall energy. And this factor, you know, depending on the value of theta, depending on the material you have in hand, always going to be between 0 and 1. So what does this mean to the value of the heterogeneous nucleation energy?
It's easier to form the heterogeneous cap than it is to form a spherical homogeneous nucleus.
Exactly, because the energy cost for this, because, you know, I just write down everything here, but if you look at the original plot that we had for the nucleation, right, this is going to be my homogeneous nucleation curve. Does that make sense? Right, so I have, you know, a huge energy barrier, but then what is the relation between the homogeneous and the heterogeneous nucleation? I multiply the homogeneous nucleation equation, this whole curve, right, by a factor which is typically much smaller than 1. Okay, for normal theta, if you think about theta, it's typically very small, right? So this whole function is very small compared to 1. So basically, this means that, you know, you keep the shape of the curve the same, you still have this one local maximum, okay, but you significantly bring down the magnitude of the value for this guy. Does this make sense to everyone? You just multiply this factor, rescale all the curves, and you're going to significantly bring down the energy barrier. Okay, so, and this is, you know, if you plot that, this is basically what you get. And if you look at energy barrier and look at some mathematics for this, okay, so the nucleation, the critical size of the nucleus is going to remain the same because you only change the, you know, you do not change the actual value for, the overall shape of the curve, right? You just bring the actual value down, you compress the curve. So you didn't change the location for the local maximum, right? And you can easily see here, because this is a function of theta, it has nothing to do with the radius. So when you do the derivative with respect to this whole energy functional, you get the same value for R star, which is 2 RSL over del GV. So this remains still the same. But what happens to the actual energy barrier? Okay, so if you look at this, okay, what this term, this is the term for the energy barrier for the homogeneous nucleation case, right? I call this del G star homogeneous. And this is the overall, you know, this is a nucleation barrier for the heterogeneous case. And you will see that these two are differ by a factor of theta, S theta, and S theta is a very small number. Okay, so this means that in the case of a heterogeneous nucleation, you know, you still work with the same nucleation, you know, same critical nucleus size, but the energy associated, energy barrier, you know, required to form a small nucleus of this particular size going to be much, much, much lower than what you need for homogeneous nucleation. Does this make sense to everyone? Okay, now what is the consequence for, you know, having a much lower barrier, energy barrier? Okay, the consequence is that if you do that homogeneous nucleation analysis, again,
we plug this energy consideration back in the nucleation rate, right? We know that this is going to depend on the Boltzmann factor, and because now you have a much lower this energy barrier here, so your heterogeneous nucleation is going to occur much faster than the homogeneous nucleation. Again, the shape will look very same, but you actually had advantage of a S theta factor, much smaller factor reduction compared to the homogeneous nucleation. So we can just focus on the bottom plot. So this is the degree of supercooling. So as you increase supercooling, you will first certainly see a lot of heterogeneous nucleus form, right? Way before you see the homogeneous nucleus form. So that's why you see that in the typical nucleation processes, the heterogeneous nucleation is dominant because it can occur at a much lower degree of supercooling. Okay, does that make sense to everyone? Okay, so again, I would just move on because of the time. I'm sorry that I used too much time to talk about Gibbs-Thomason effect, so I use some of your time here. But just want to give you two examples. Okay, I think I will revisit these later. But you know, these are two examples of heterogeneous nucleation. Okay, and I think this one is a little bit trickier because let's look at this one, because I think we have a lot of students from Intel, so I think it's helpful to use this example. This is a tin joint actually connecting two, I think, copper wire together, and you can clearly see that, you know, these are not a single grain. These are a lot of grains that are very thin, you know, in this very anisotropic direction. Okay, and also you can see from this side. So this implies that, okay, you know, and these grains are bulk grains, very large in size. These are very smaller grains, but many of them. So this means that we actually have deposited this liquid tin in between these two copper wire. On the interface, you have a lot of small solids that already form, tin solid form, and then they grow in this direction because they're all kind of impingement on one another. So they can only grow in this direction away, and the same on this side. Okay, and only probably during the, you know, certain time, and there's some large homogeneous nucleation occur in the middle, and then they start to grow. Okay, so that's why you see this very heterogeneous crystalline structure. But again, I'm sorry that I used a lot of your time already after class. I will stop here. Okay, so I'll stop recording.